Welcome to chapter 16, acids and bases. Now that we've gotten a really good hold on thermodynamics and kinetics, we're going to talk again about acids and bases and their ability to drive a specific chemical reaction, the acid-base reaction or neutralization reaction. Some of these reactions are going to be straightforward and forward reactions only. Some of them are reversible reactions. We've spent some time in acids and bases before last semester. However, we're going to dive even further into those equilibrium reactions and be able to do ice tables for all of these if necessary. So the idea of equilibrium will still be present. We are now just going to be looking at a specific class of molecules, acids and bases. Now, acids have some general properties. The first one always makes me laugh: sour taste. Do not taste chemicals, but things that we definitely can think about that we taste that are acidic are things like lemon juice, citric acid, acetic acid, if you drink vinegar, if that's your thing. All of those are acids. Hydrochloric acid is a very strong acid. Y'all maybe have seen that in laboratory as well. The ability to dissolve many metals is one of our general properties as well, and the ability to react and neutralize bases. We also see that when we use blue litmus paper, we change it to red. So there is something about the pH scale that we will talk about later. Here are some common acids and their uses. HCl, I believe, is one of the most prevalent in chemistry labs. It's also the primary component of your stomach acid. So how your food is digested is from hydrochloric acid. Sulfuric acid and nitric acid are used more in production type chemistries. We might not have seen them. Maybe hydrochloric acid or sulfuric acid is in our lab, but not as readily as hydrochloric acid. Acetic acid is household vinegar. It is the main component of vinegar. You just add a ton of water, and that's the one that you find at the store that you can buy. Citric acid is found in lemons and limes. It is one of the more natural ways to adjust the pH of food beverages. Carbonic acid is found in carbonated beverages. So we just bubble carbon dioxide into water and you make carbonic acid, and that's what gives us that lovely carbon dioxide bubbly feeling in sodas. But it's also one of the reasons why you need to drink lots of water or brush your teeth after you drink a soda, so that that acid doesn't stay on your teeth and start wearing away your enamel. Hydrofluoric acid is used in a lot of different things: metal cleaning, glass frosting, etching. It's not often found in general chemistry labs. Hydrofluoric acid is one of the weirder chemicals. It won't burn your skin like HCl or HBr will, or H2SO4. It's not as reactive as those first three that we see on this list, but it does readily decompose your bones. So don't touch it, because it will go straight through and just start eating away. Super fun. Phosphoric acid is also another one used as a biological buffer. We'll talk about buffers at the end of chapter 17, but phosphoric acid is used more in biological systems. Some structures of organic acids. We've seen these guys before. We're just going to talk about them more often now. Carboxylic acids is a functional group. Now we know that typically acids have that hydrogen there, and it's highlighted red for us on this lovely slide. But the specific carboxylic acid functional group is one where we have a carbon double bonded to an oxygen and single bonded to an OH. I'm going to draw that Lewis structure. And then there's always something on the other side. But this functional group right here is very, very common in organic chemistry. This is the functional group that gives acetic acid and citric acid its acidic nature. Only the H atom in that group is considered acidic. So when we are talking about an acid, traditionally we are talking about a proton or a hydrogen. In COOH, it's the H. And the other group that gets to appear over here is other carbon or alkyl groups. You'll learn about all different kinds of alkyl groups and carboxylic acids in organic chemistry. Now, bases generally taste bitter. They're alkaloid. They are often poisonous. These generally feel slippery to the touch. So if you've ever gotten a strong base like Clorox bleach on your hand and you felt your skin really, really slippery. The reason for that is it's hydrolyzing your skin cells. So that's fun. Go wash your hands. It also has the ability to neutralize acids. So we'll see acids and bases are meant for each other, kindred spirits, and bases can change red litmus paper to blue. So there is, again, a spectrum of pH that we'll talk about at the end of this chapter. Sodium hydroxide, potassium hydroxide, they're all very common bases that we've seen. Sodium bicarbonate is baking soda, an antacid. It's the source of carbon dioxide. It is a base, as well as sodium carbonate that is used in water softening. So if you have a water softener in your home, that's usually using some sort of salt. Typically, they can be sodium chloride, but they also can be sodium carbonate, which is a base. Ammonia is what we call an organic base or non-ionic base, a covalent base. NH3, notice that there's no metal coordinating with that. It's just nitrogen and hydrogen, which are both non-metals, so therefore it's a covalent molecule. Ammonia is used in detergent and lots of cleansing products, but it is still considered a base as well. All right, let's talk about the hydronium ion. H plus ions, we're going to use that terminology or that denotion. H plus meaning hydrogen has lost an electron. Well, we can call it a proton because think about what is in hydrogen's nucleus. A proton, no neutrons. Hydrogen isotope that is most prevalent is hydrogen 1. So it has a proton and no neutrons. And when it loses its one electron, it's all that's left is a little nucleus with a proton in it. So we use that interchangeably, H plus ions and protons. Now they are produced by an acid, so reactive, and they are so reactive, they cannot exist by themselves in water. All right. So if you were to imagine H plus hanging out in a solution with water, it's not going to be by itself. Instead, water is going to use one of its electrons from the oxygen atom and go pick it up. And we're going to be making hydronium, the polyatomic anion H3O plus. Notice that that oxygen gained the positive charge that the cation, the proton, had. By picking up that extra proton, we have combined and stabilized the overall idea of the H plus proton to make it H3O plus. We often simplify it just by writing that H3O plus functional or formula right there. We are going to use it interchangeably with H plus. We will not use the complex formula. That's way too complicated. We have multiple definitions of acids and bases. We've talked about the Arrhenius definition. It is the simplest and most restrictive. Acids are substances that when dissolved in water produce hydronium, and bases are substances that when dissolved in water produce hydroxide. And so when we look at that definition, now Arrhenius, rightly so, this was his definition for acids and bases was his PhD thesis. And way back in the day, it was not very widely accepted. I think that's when they still use the definition of acid as something that tastes sour. But they slowly over time and with more work, they did award Arrhenius his PhD. And this definition is still utilized today. The Bronsted-Lowry definition is a little bit better. It's based on reactions in water, but utilizes the definition that acids are substances that when dissolved in water donate protons. All right, they donate an H plus cation. Bases are substances that accept protons. Notice that it's focused on that H plus rather than separating an acid or a base. Right? They're connected now. The Lewis definition is the most expansive and based on a lot of electron donation and acceptors in reactivity as well. Acids are substances that accept or need an electron pair. Bases are substances that donate an electron pair to another substance. We will be mostly looking at the Bronsted-Lowry definition, but we will introduce Lewis as well at the end of our chapter. Arrhenius theory was developed to say that acids produce H+ ions in an aqueous solution. So we can think about HCl. HCl is not an ionic bond, but it reacts much like one in that it produces H+ ions and Cl- ions when in an aqueous solution. With sodium hydroxide and other bases that produce hydroxide ions in an aqueous solution were salts, an ionic compound that specifically had hydroxide polyatomic ion acids anion. Now the H+ ions from the acid combine with the OH- ions from the base, and what do you think? H2O, right? H+ and OH- makes H2O. We can think about that same way in a type of curved arrow reaction here. Hydroxide would have extra electrons, and it says, hey, I'm going to go donate them to pick up the hydrogen. That arrow, let's highlight it blue. This arrow specifically is talking about oxygen going to make a new covalent bond with the proton. By donating one of those lone pairs, oxygen goes back to a formal charge of 0. By accepting that lone pair, hydrogen cation, the proton, goes to a formal charge of 0 as well. So we can see a lot of different definitions in this Arrhenius acid-base definition as well. Things like donating electrons and accepting electrons, the Lewis acid-base reaction. Now, why we call it a neutralization reaction when an acid and a base come together is because the cation from the base, such as the sodium from sodium hydroxide, combine with the anion from the acid, like the Cl- one from HCl, and they make a salt. Water and salt, that's pretty overall neutral, right? So when we're looking at something like H and Cl and Na+ and OH- coming together, as we are making water in this reaction, we are also going to create that ionic bond. There's our water forming, plus Na+ and Cl-. Excellent. Chlorine started with 3 lone pairs, and when that bond breaks, it takes a 4th lone pair. There are some problems with the Arrhenius theory. It's too narrow of a definition. The theory does not explain why molecular substances like ammonia act as bases as well. It does not explain how some ionic compounds such as sodium carbonate or sodium oxide dissolve in water to form basic solutions, even though they don't contain hydroxide ions. It also doesn't explain why carbon dioxide, when dissolved in water, forms an acidic solution, even though it contains no H+ cations or protons. And so we see a lot of holes, all right? But this was a long, long time ago. And so what we can do from here is move on to the next theory, the Bronsted-Lowry acid-base theory. The Bronsted-Lowry acid-base theory defines acids and bases based off of what happens in the chemical reaction. It locates that proton that is being transferred, and it talks about whether the proton is a donor or an acceptor of that proton, or whether the molecule is a donor or an acceptor of that proton. Any reaction that transfers a proton from one molecule to the other can be classified as an acid-base reaction, whether it occurs in the presence of water, an aqueous solution, or if there are even any hydroxide ions present. So the Bronsted-Lowry definition really expanded the definition of a base, focused on the proton transfer as the focal point of the definitions of the other components in the reaction. All acid and base reactions that fit the Arrhenius definition also fit the Bronsted-Lowry definition. So the Bronsted-Lowry said the acid is a proton donor and the base is a proton acceptor. Base is going to donate some electrons to go make a new covalent bond. There's the accepting. And the acid is going to say, okay, bye-bye proton. I'll take your electrons and I'll go be an anion over there. All right. So we do see charge balance. We start with things that are net neutral and we will make overall net neutral, right? But one is negatively charged and one is positively charged. Now, Bronsted-Lowry acids are proton donors. Any chemical substance that has an H atom can potentially be classified as a Bronsted-Lowry acid. When HCl dissolves in water, the HCl acts as the acid because the H transfers from the Cl to the water to form hydronium. Water acts like a base so that it is accepting the proton. Here's that reaction again. Let's just do it in the form of our arrows here. Oxygen as a base picks up that proton. It's going to make a new bond with it. Well, hydrogen can't make more than one bond, so the Cl has to leave with that electron lone pair. We are transferring H plus, not the electrons from the HCl, just the proton is going to go over here. So we get H3O plus and Cl minus. Now what we get to say with this is do a little bit more development of names. Acid has the proton. Base, we'll notice, has those electrons, has those things to make a new covalent bond. What forms when the base picks up the proton is what we'll call a conjugate acid. And what happens when the acid donates a proton? It becomes the conjugate base. Same thing for bases. Bases are proton acceptors. And so when any chemical compound has an atom with lone pair electrons, it can be potentially referred to as a Bronsted-Lowry base. Often one atom in a molecule is more than willing to accept a H plus ion and from a transfer based off of its molecular structure. So when NH3 is dissolved in water, the NH3 is the base because it has a lone electron. Let's write out the Lewis structure for NH3 just to remind ourselves what it looks like. Same with water. In this case, NH3 is the base and water is the acid. Nitrogen is a very, very good base. It likes to pick up extra things. It can become positively charged. What that does for us is it makes NH4. And if we did the formal charge here, we'd see that it was +1 and hydroxide -1. We again have the base becoming a conjugate acid after it picks up the proton, and the acid becoming the conjugate base once it donates the proton. Water can act like both an acid and a base. Super cool. One advantage of the Bronsted-Lowry theory is that it illustrates equilibrium reactions to be as followed, right? Acid and base can be in equilibrium with the conjugate acid and the conjugate base. Sometimes we don't even care about these conjugates, right? We just kind of want to think about what's an acid on the reactant side, what's an acid on the product side, and things like that. But we can use conjugate just to make sure that we know which side of the reaction we're talking about. But just so you know, if the reaction was reversed, that the conjugates could become the original or the reactant acids and bases. Notice that this reaction is now flipped, and the conjugates are themselves able to also act as acids and bases to produce the original reactants. So whereas the forward proton transfer occurs, the backwards proton transfer can also occur. The original base becomes the conjugate acid, and the original acid becomes the conjugate base. each reactant and product, is called a conjugate pair. Notice the difference. A base is adding an H plus cation, so you increase the charge by 1 positive unit and increase the H count by 1. And for an acid to become its conjugate, we are subtracting an H ion. So H2O becomes OH, and the charge was neutral. We subtract 1, and that's why we get a negative. The base will always accept the proton and become the conjugate, and the acid will always donate a proton and become the conjugate.